This is the second lesson in this course on fluid mechanics in medicine. The topic is Archimedes' principle and buoyancy. The learning objective is to apply Archimedes' principle to understand how the buoyant force affects objects that are partially or completely submerged in a fluid. Archimedes' principle, named after the ancient Greek mathematician who, according to legend, discovered it while getting into a bathtub, states that any object, wholly or partially immersed in fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. What exactly does this mean? Imagine a glass or tank of water into which some object is fully submerged. One of the two major forces acting on that object is the force of gravity, pulling it downward, which we call its weight. You may recall from classical mechanics that the weight of an object is equal to its mass times little g, which is equal to the acceleration due to gravity as measured at the surface of the Earth. The other major force acting on the object is its buoyancy, or the buoyant force, which pushes it upwards. The buoyant force is equal to the density of the fluid times the volume of the fluid displaced by the object times g. Whether or not an object sinks or floats depends upon the balance between weight and buoyancy. Neutral buoyancy is a special situation in which an object's density is equal to the density of the displaced fluid. In other words, its weight is equal to the buoyant force. As you might expect, in this circumstance, the object may seem to hover within the fluid. Let's look at an example of using buoyancy to solve a physical problem. What acceleration will a completely submerged object experience if its density is 3 times that of the fluid into which it is submerged? So density of the object equals 3 times density fluid. From classical mechanics, we know that the sum of the forces acting on an object will be equal to the mass of the object times its acceleration due to those forces. The forces here are its weight, which will be partially counterbalanced by its buoyancy. As previously stated, the weight of the object is its mass times g, and the buoyancy is the density of the fluid times the volume of displaced fluid, in this case the same as the volume of the object times g. We know from the last lesson on density that the density of an object is equal to the mass divided by its volume. So therefore, the mass of an object is equal to the density times volume. And remember that the density of this object is 3 times the density of the fluid. So for each mass of the object, we can substitute 3 times density of fluid times volume of object, which results in this. The density of the fluid is present in every term, so it cancels out, and the volume of the object also cancels out. This leaves us with 3g minus g equals 3 times the acceleration of the object. Solving for a, we find that it's 2/3 g, and of course g is a constant that's equal to 9.8 meters per second squared, which results in an acceleration of 6.5 meters per second squared. This solution is interesting because it highlights that the acceleration of a submerged object is only dependent upon the relative densities between the fluid and object, and is independent of the object's mass and volume. Let's look at another example. Imagine we have an open wooden crate floating on the water, and for some reason we want to put our collection of Michelangelo's David replicas into it. How many 2-kilogram David replicas can be placed into the open 30-liter crate that it itself is 10 kilograms in mass without the crate sinking? The first thing to realize is that each statue that is added to the crate will lead to the crate riding lower and lower in the water. The crate will sink once the water reaches its lip, so the maximum displaced volume of water before sinking occurs is equal to the total volume of the crate. Another way to look at this is to say that the weight of the crate plus that of the maximum number of statues equals the weight of the maximum volume of displaced water. So the weight of the crate is the mass of the crate times g. The weight of the statues is n, where n represents the maximum number of statues, times the mass of each individual statue, times g. And the weight of the maximum displaced water is the density of water times the full volume of the crate, times g. As happens with many buoyancy problems, G cancels out. Now let's enter in the specific numbers. The mass of the crate is 10 kilograms. The mass of each statue is 2 kilograms. While we could calculate the product of the density of water and the volume in terms of cubic meters in order to get the water's mass, we could also use an important relationship from the last lesson. The mass of 1 liter of water is 1 kilogram. Therefore, the mass of 30 liters of water is 30 kilograms. Solving for n, we find that n is equal to 10. So with 10 statues added, the water level will reach the lip of the crate. In reality, since the water probably would not be perfectly still, some water would creep into the crate here and there, and once a little water had gone over the edge, the weight of the crate and its contents would increase, pushing it further down, resulting in an exponential increase in water accumulation until it sank within a very short time frame. So realize, even if the math tells us our crate boat can handle 10 statues, you would not attempt that in real life. And speaking of real life, how does buoyancy apply in medicine? I don't know of any circumstances outside of diving medicine where one would need to literally calculate buoyancy. However, conceptually, buoyancy is critical to the body's functioning. One of the more important ways in which this is true occurs up in the head. So here's a skull, and inside the skull sits the brain, of course. What many people don't realize is that the brain does not just rest in the skull like it's sitting in some otherwise empty box. Rather, it's encased within a membrane containing something called cerebrospinal fluid, or CSF. The CSF has a number of functions, such as cushioning the brain during closed head trauma and serving as a microbiologic and physiochemical barrier. But the most crucial function is arguably related to the fact that the density of the brain is almost the same as the density of the CSF. This allows the brain to float within the CSF. In other words, it's an example of neutral buoyancy. Why this is so critical is that without the CSF and without the buoyant force on the brain, the bottom of the organ would get compressed by the overlying weight of the rest of it. This compression would cut off blood flow, leading to the death of neurons and eventually death of the patient. That's it for Archimedes and buoyancy. The next lesson will introduce the concept of hydrostatic pressure.